Well, first, I just want to say I'm really honored and humbled to be here and to have been invited to give a talk today. I've been here for most of the talks earlier, and they've actually been spectacular, and now you get me. So sorry about that. Um, and the other thing, I thought, it's kind of late afternoon, you're getting bored, and they put this on me, and I thought I might do the dance that the people did this morning at the show, but then I decided against that. I actually hurt my toe, so I can't do the dance. Anyway, so yeah, behind the scenes, Intel Rendering Framework and Academy Software Foundation. So why did I pick behind the scenes? Well, again, we've had a lot of great talks, some of the GPU usages that we see coming on, that kind of thing. But today, a significant majority of your movies and are rendered with the help of Intel software and hardware. So sort of behind the scenes of Corona and V-Ray and Cinema 4D and Moonray renderer is Intel software and hardware technology. Many of you may have heard the term Embree. Philip brought it up earlier. There's more to Intel's rendering capability than just Embree, and I'm going to talk about that. Anyway, we've had a lot of fun with Thanos today, and lo and behold, the V-Ray and Digital Domain and Marvel got the benefit of Embree's rendering of Thanos, so that's why that's up there. So I'm going to kind of give some context. So today's visualization and rendering world, as we've talked about, many of the customers here, or many of the speakers rather, goes everything from the highest quality offline rendering. That's typically what people's head goes when they think about Embree and they think about CPU-based rendering. They say that's for when we do all sorts of hours per frame, as Philip was saying. And then you kind of start moving across the spectrum of interactive towards real-time rendering, all the way down to gaming. So these are all the areas that are touched in some form or another by rendering. The middle having sort of grown up from, where it says interactive, that's really only been in the last 3 to 5 years, depending on the technology that you're talking about. On the right, as Steve mentioned this morning, rasterization is the technique for highest performance today. And then ray tracing has been considered the technique for highest visual quality. So that's kind of a context setting. We'll come back to that later. But the proven approach today for maximizing your flexibility, your performance, your cost of operation, and capability, there's really a reason, a legitimate technical, operational, and performance reason that CPUs are the prevalent software. We call the notion around what Intel Rendering Framework does and these open source software initiatives, software-defined visualization is a term you may or may not have heard, but just like software-defined networking and the notion of the flexibility that you can get from a hardware system. In this case, and in our case here, up there, is, that's a traditional kind of look at a data center or a pictorial of a data center. And, most of these data centers do not have GPUs in them, and particular render farms and some of the offline render cloud. There are some, adders to GPUs where they make sense, and that's all cool. And by the way, I don't want to say CPUs are the only thing, because soon I'm going to be talking about some of our GPU plans as well. But the bottom line is for today, the proven approach really is CPUs, and reasons are up here on the right. We provide high fidelity. Remember that most of these systems, workstations through data centers, are parallel computers. They are highly capable parallel processors. The GPU is not the only thing that's a parallel processor. All Intel processors for the last 10 years have been pretty much parallel processors. And if you keep hearing increased core counts, I'll actually show you some core counts soon. But that's, keep this in mind as well. The current kind of state of the art is something around this, where you have a data center capability, you may have a workstation as well, and you either direct connect or use cloud or say a local on-premises, as the gentleman from Google was talking about. This is a quick snapshot or a detailed snapshot of what Intel Rendering Framework means. These are all libraries, basically. OSPRay is a little bit of a different animal, which I'll talk about a little bit more. But we have Embree, which many people in the studio industry have heard. It's an open source, high-performing, highly tuned set of geometric ray tracing algorithms, the broadest feature functionality in the industry. OSPRay, I'm going to talk a little bit more about, but it's what we call a scalable rendering engine. It is targeted at interactivity in real time. A lot of people maybe don't realize that, but it's basically the way that we take Embree and we turn it into a interactive to real time engine. And it's been on the marketplace for quite a while. So when you hear that, Steve talking about, hey, great, we started real-time ray tracing last year and everything. OSPRay's been in the market doing real-time and interactive ray tracing since 2015. So it's not new. And that capability at product level, OSPRay is a product. It's an Intel product. So it's also, to Philip's point, he's doing a lot of great work and has done a lot of great real-time work. And in fact, we even heard much of it from his team members. I completely agree with that. And some of those techniques have actually made it to the market through Embree OSPRay, are the capabilities. I'm going to hold off a little on Open Volume Kernel Library. It's something that's coming. Just wanted to give you the heads up on that. We'll talk a little bit more about that soon. Open Image Denoise. Again, this is something we just launched in February in a beta form, and it is getting tremendous uptake in the industry. It's a fantastic denoiser. Attila Afra, the lead developer of that. I was going to say he's the lead, but he's pretty much the only developer too, which is pretty amazing. He's here. He's going to talk about that. And then a lot of people also don't know about this thing called OpenSWR, which stands for Open Software Rasterizer. Now, most of my talk's going to be about ray tracing. Lots of the talks here are about ray tracing. Steve Parker brought it up that, hey, rasterization's still good, going strong. Well, we actually have a CPU-based rasterizer that is quite impressive, and we'll talk about that. This is kind of how, from a coder level, how you would consider and how the two major implementations that we've seen in the marketplace. So you have, again, this would be V-Ray and Corona over to the left, what we call the professional rendering stack. You've got your application. In the case of V-Ray or Corona, you could think of this as Maya or one of the higher level applications that provides the user interface. The renderer would be V-Ray, and then they're built on the Intel kernel library. Soon they'll be able to incorporate the volume kernel library if they're into volume rendering. And now many folks are adding Open Image Denoise for that denoising capability. Some of the cool pictures that Steve showed, and I'll show you some, and Attila will as well. And then you have, in this case, our typically a Xeon processor or higher end parallel processor in workstations and render farms and servers. And then this thing I'll talk about, Intel XE architecture, which is the broad architecture name for our CPUs. And then we do a lot of scientific rendering. You could call this a general visualization stack. And the main difference there is a whole slice of integrated OpenGL. So I'm going to give you an overview. Just keep in mind this is a way to get a lot of this information. Our landing page, Intel RF for rendering framework. So OpenSWR, I just talked about it. High performance rasterization. Is there a problem? Oh, okay. It's only a problem that I can see. You can't see it. I don't think. Yeah. Okay. So OpenSWR, again, a OpenGL capable system. It's all open source. Everything I'm going to talk about is fully open source, fully available, down to the metal, as Philip was saying earlier. You can see every algorithm, every implementation across our vector processors. It's upstreamed to the Mesa 3D project, which is known as the kind of main CPU. It mixes in GPUs as well, but it's the open source full OpenGL stack. Today we focused primarily, up till today, primarily focused on OpenGL, that scientific rendering stack that we have here, enabling this for key visualization apps like ParaView and Visit. These are heavily used in scientific rendering, so we only needed to support up into OpenGL 3.3. Actually, with the advent of cloud and the type of things that the Google Visual Cloud and other elements, we are finding its success and its capability is going to drive us to make it a fully modern OpenGL that would be available in a cloud environment that say does not have a GPU. So you won't have to buy the expensive GPU instance. You could actually run OpenSWR if that meets your needs. Wrong way. So this is an interesting chart, and this kind of really gets at, it's more than just the OpenSWR story here. This is the story about extracting parallelism on CPUs. Again, remember I said CPUs are parallel processors. So this little thing, I can't see if you see it, this little yellow line is something called LLVM pipe. It is the default renderer that comes when you download Mesa and build it and you run it on a GPU. We are orders of magnitude, 2 to a little more, orders of magnitude faster on the same processor with the same driver or OpenGL driver, but all you do is you add an environment variable before you start that says gallium_driver equals SWR, and if you do that, you get 200 up to 150 to 200x performance on a Xeon platform. So this takes it from its traditional history has been as either a tiny, in very small increments, tiny data that could run interactively, maybe 1 to 2 frames per second, or as a batch job where you render off the back and it doesn't matter how long. OpenSWR takes your whole system, your whole environment, and makes it an interactive system for OpenGL rendering. We typically get anywhere from 10 to 30 frames per second. So that shows you that same platform. And by the way, LLVM pipe is not a serial implementation. It is a parallel implementation as well. We just took it a step further and really optimized it for the latest Intel technology. So this kind of shows you where I'm also going with Embree and OSPRay and the other CPU-based things. Because it's on a CPU does not automatically mean it's slow, or even slower than a GPU implementation. Embree. Many of you here, I think, know Embree. It's our optimized ray tracing kernel library. As I said, it is one of the key behind-the-scenes engines, if you want to call it that, or hearts or lungs, key things that many of the studio renderers, as well as the CAD and interactive renderers we talked about, have adopted. This is just some of the stuff that runs with Embree, including the Grinch movie that came out from Illumination. Also, Secret Life Pets of 2, which is out in the movies now, is a Embree at its core. And Corona, we've had a great relationship for the last 10 years. Corona has adopted Embree. Again, look for Attila's talk. He's going to talk more about Embree. This is another Corona image from Embree. Now, my fear with putting this image up was that you're all going to run out and go for a drink now. But remember, this is a 3D model. This stuff's not actually real, so you're not going to go out there and find, red and purple drinks out there. But please hang in a little longer with me and hopefully with Attila. Just to give you a sense, this is some movies. These are movies that have public information that says they were used with V-Ray and with Embree from the various studios here. So as you can see, as I said, the state of the art and the best movies and animations and visual effects typically are using something like V-Ray and Embree. So it's not a short list there, and that's only some of the movies the last 2 years. Again, more Embree. The whole Moonray DreamWorks environment was built from the ground up to take advantage of Embree. So How to Train Your Dragon: The Hidden World was their first Moonray full end-to-end movie. They actually were using Embree for a number of years for lighting tools, a lighting tool called Torch, but they moved it to their full-blown capability. And then finally, this is something that Attila will touch on. One of the things that we've really focused on through work with Weta Digital and DreamWorks and Illumination, Frame Store, many of the people use Embree, is hair. Everybody loves hair, apparently. I hope mine stays on a little longer. Hair for, so there are six different algorithmic geometric shapes that allow us to do hair, grass, and all those capabilities at very high performance. Attila will talk more about it, but it is just, this is where we meant about the breadth of features and capability that we have to enable the movies to happen and to enable visual effects to happen fast enough so they can actually deliver a movie, in a few years. Open Image Denoise. I'm pretty much going to leave this to Attila. You've got the expert here, but it is our AI deep learning based denoiser. Actually, I want to take a step back on that. Our first algorithmic launch in Open Image Denoise is an AI deep learning denoiser. Works really, really well. I don't necessarily think they're announcing anything big here, but I think if you've seen Ondra online showing the integration in Corona 4.0. So Open Image Denoise will be available in Corona 4.0 when they release it in a few weeks. I can't speak for the V-Ray folks, but I'm pretty sure they know about it. Again, wait for Attila. He's going to show you some really cool stuff. I'm just going to show you a teaser. Anybody recognize this image? If you're here this morning, you saw the Sponza image. This is what that is. This is the original at 16 samples per pixel. This is when you add Open Image Denoise to it. Attila will talk more. He had this in his slide deck. He took it out and put other cool stuff in. Okay, now the newest thing that we're doing is taking feature functionality that we originated in our OSPRay library, which has been a very strong volume rendering library, but the last 2 years it also has a full path tracing capability that is being used, and we're going to talk about that more in a second. But all the stuff you see here are images that have been done with the techniques in OpenVKL. Think of it as a peer for volume rendering to Embree, so a low-level volume integrator, ray tracing capability. My team doesn't want me to tell you this, but I will just because I feel like it. We will be implementing volumetric path tracing in our path tracer in the next 3 to 6 months, and the early images are spectacular. Anyway, think of this as a peer to Embree, many different formats. OpenVDB is the format of choice. We have not implemented that yet in OSPRay. What we're doing is taking all the capability out, and we're actually going to be launching something called OSPRay 2.0, which is going to have a lot of cool new capabilities and more extensibility, and will include use of OpenVKL, but you're not required to use OSPRay to use OpenVKL. This is a code class, so I thought I would throw some code in, but you guys can, I'm sure all you great programmers can just look at it and know exactly what's happening there. But the idea here is we have kind of a model that we write almost all our code in. So these VKL, et cetera, capabilities are, you know, a streamlined interface, make it easy to understand and use. In this case, this little loop generates and delivers a volume like that from the data. The other thing that we care about, particularly in scientific viz, is something called isosurfacing. That's extracting a particular value or element, for instance, heat, and heat or magnetism or any physical property. And so volume renderers often have to do essentially a kind of surface rendering capability and integrate it. And so this is a capability that will come out of the box. You can combine volume and isosurface rendering. And again, our path tracer will combine geometric and volume rendering all in one. OSPRay. I'm going to take a little time to talk about OSPRay. Attila's not going to talk about it, but it is very cool. A lot of people, I won't say wrote it off, but when they first saw OSPRay, they go, "Oh, okay, crap. This is just for scientific visualization and volume rendering. I'm not going to look at that now. Embree's my choice for that." Well, that's actually not true. That was what we started out with. But as I said, OSPRay now is in several products doing full path tracing. What OSPRay does, though, is it provides a higher level rendering infrastructure. So if you're DreamWorks or your Chaos group, you might selectively use OSPRay in certain scenarios, particularly what I would call interactive or real-time preview. Okay, lower sample per pixel, but you really want to see the whole flow, the lighting, the capability. But OSPRay implements certain, shaders and materials and other things that V-Ray and DreamWorks actually consider their value add or their secret sauce. We don't want to take that away from anybody. That's why Embree is completely available to do that. But there are some really cool things that OSPRay can do, for instance, over and above what optics can do. So it stands for Open Scalable Portable Ray Tracing Library. Don't tell the Intel branding people that because they don't like things that actually say words, but I got it through. It is a higher level rendering API. You can think of it as the ray tracing API equivalent to OpenGL. That's how you would approach it. It doesn't map to OpenGL. You can't do it, but from a conceptual context, it's OpenGL kind of with the considerations for general ray tracing and capability, and it's been written from the ground up. So again, very cool API. You can do 3D geometry or volumes or both or integrate them. The other thing that's about OSPRay is it's more than just an API. OSPRay is an SDK to help enable the development of a variety of visualization apps, or visualization capability, I should say. And that's how many of our vendors have. And then thirdly, it is a customizable plugin environment where you can put in custom geometries, custom management of your flow of data. Okay, we've created a production-worthy but lightweight visualization app called OSPRay Studio, all open source. So you can actually start with OSPRay Studio, then create some magical app that you want to do. We're not, trying to sell it. We're trying to provide capability. And then it leverages Embree, Open Image Denoise, and soon, it's not on here, but OpenVKL. This is some of the traditional stuff that OSPRay's known for. One of the interesting ones is this one up here. This is a combined path traced car. Now it doesn't have great features in it, which is fine. That was the intention. And then volumes overlaid with streamlines. This is a computational fluid dynamics or an airfoil or wind tunnel, if you will, virtual wind tunnel. Again, Philip was talking about the varieties of use. The guy in the upper left is what we've done with Stephen Hawking and his team. We're still working with them. Dr. Hawking unfortunately passed away last year, but we've been working with them a long time. And then again, Philip mentioned oil and gas, and this is a seismic image from the Moroccan oil shelf. So this is kind of the thing to realize is the work that everyone in this room has been involved in creating entertainment and reality and digital twin manufacturing is actually being mapped to science because a scientist is a human. And as Steve was talking earlier, we take cues from various things. And so putting a shadow, I think I have another picture of this guy here with a shadow on it. You know, like, why would a scientist want to simulate a thing with a shadow? It's because it appeals. It's even to them, and they can see more nuances when you put this stuff in here. So that's one of the reasons why OSPRay got there. But the other thing to realize is it's fully scalable, and by that I mean, if you want to run it on your laptop 4 cores, you're going to get a certain performance. It'll try to maximize that performance. You want to run it on a workstation with a single or dual socket Xeon, you're going to get that X amount more performance for rendering. The other thing it does, though, it can go across multiple nodes and utilize the memory size and the compute performance. And our benchmarks, at least for the rendering side, not shading, it's essentially linear scalable. If you know the clock frequency and the number of threads that you can do, and by the way, it's number of threads, not number of cores, that you would multiply. So the more threads it gets, the better it goes. You would get a sense of its capability. And that's what I mean by, since 2015, we've been able to do up to real-time rendering, because you give this thing 32 nodes of a cluster, it'll render it 32x faster than one of the nodes. And that will drive it into the 60, 70, 80, or 100 frame per second with a Bentley car. So this is a path-traced Bentley car. We ran this at SC17. So again, real-time before RTX capability. Now, we also did this remotely connected to something called Stampede 2. If you heard Steve Parker this morning, he mentioned the Summit supercomputer as currently the highest performing one. Stampede 2 is the second highest performing supercomputer in the United States. We were on there with our processors, and we worked closely with that team there. But we were able to render this Bentley at up to 100 frames per second when we threw 128 nodes at it. We've actually tuned better since then. Another thing is real production assets. So remember I was saying, a lot of people thought SciViz rendering, that's really cool, great, you're helping scientists. As far as I know, we're the only commercial product that can actually render the Moana scene at any kind of frame rate from Disney. So this is the full Moana scene. It has 160 billion primitives with lots of instancing, as you can see. And we ran this with OSPRay on 8 dual socket nodes with denoising on a single node at 10 to 15 frames per second at SIGGRAPH last year. So interactive, full production asset. This is after we tooled around with the data a little bit, it ended up being 100 gigabytes of data. So 2 RTX 48 gig parts could not run this. Watch this, and I'll tell you about this in a second. Or I can tell you now. So this is the Moana scene. This is a live screen capture. This is also connected over a network from Oregon to Austin. So we're screen capturing in Austin, a connected version of this. Again, this is running at the 10 to 15 frames per second manipulated. If you saw the Google talk with the V-Ray 4 nodes with 8 GPUs, everything else like that, this was actually a much cheaper environment. We were running denoising there. We're running heavy lighting with shadows and ambient occlusion. And again, the full capable Moana scene. Intel Rendering Framework, while that name is about new, it's about a year old. The various components are not new to those people in the know. These are just a handful of the companies that use it. We should add Unity up there. Unity just announced Open Image Denoise integration. Again, our friends, cool car pic with Corona. That picture is about 5-6 years old. Yeah, so we're well trodden in what we've been able to do, and I don't believe anybody complains about our quality or capability. Everyone complains about performance all the time, so that's fine. Again, Xavier out at Illumination has spent the last 2.5 years with us, adopting Embree directly into their renderer, and has some nice things to say about it. USD, so this is really our first core direct foray with OSPRay into the studio industry. While we've shown OSPRay running up there, there's really, what are you going to do? Pick up OSPRay and start using it as a tool? Your designers aren't going to use that, whatever. They want to use Maya, they want to use Houdini, they want to use other stuff. So the way to do that today, to get interactive to real-time, high quality rendering right on your desk, or with your desk supported by 4 or 5 nodes of the render farm, or 4 or 5 nodes that you just put as a group capability. But USD, Universal Scene Description from Pixar, driven by Pixar. They have this thing called Hydra Rendering Framework. They implemented themselves an OpenGL renderer. They implemented and provided an Embree, a kind of tutorial renderer, and now we have a pretty robust OSPRay plugin. It is available. You can download it. If you've got a USD viewer, it should work. Just to give you a sense, again, of the idea of real-time performance. So cool. A GPU with OpenGL can do 191 frames per second on this relatively simple scene. I admit it's a simple scene, it's not a large scene. But you don't need 191 frames per second. But when you start using ray tracing, the numbers here are for a single dual socket platform. So 60 frames per second with just basic, a little bit of global illumination. Add ambient occlusion, it drops a little bit. Make it path traced, it's 31 frames per second. In this case, it's 1 sample per pixel. Sorry about the fine lines. They're not meant to fool, they're just meant to meet all my legal requirements. And then the cool thing about OSPRay and the capability of the USD viewer is we can start adding nodes to the capability, right? So in this case, what we decided to do, this is actually a very simple scene, so you got to goose things up a little. So we went to 16 samples per pixel on 1 node. That drops, now you can think of that almost instantly as adding 16 times the capability. We didn't drop 16 times, but we go to about 3 frames per second. But if you want that level of quality, you can scale up with 4 nodes, and in this case, this sort of beta version got close to 10 frames per second. And that's plenty interactive for getting full path traced image at 16 samples per pixel plus denoising. So just to hammer it home, this is the OpenGL rendered image. This would be the path trace rendered image that a creative might see. Yes, it's a cartoonish scene. This is the main scene they use for USD testing, so that's why it's here. And you may have seen it at Pixar events. The other thing that's kind of interesting, and depending on how you understand how data is distributed and delivered among studios, one of USD, which is kind of bootstrapping but getting a lot of benefit in the industry. It stands Universal Scene Description, as I said. That's so people can exchange assets, and the end result is Thanos doesn't look green, he looks purple or whatever. So this is a preliminary version. We are working hand in hand with Disney on their USD conversion. USD is a different set of files and formats. The other, the one that's out publicly is a OBJ, PTEX, lots of other traditional formats. USD has a different format, but Disney Pixar gave us the heads up to let you guys know that we are working on that for production level assets, and it's work in progress. The big thing you can see that's missing, it looks pretty good, except you don't get the cool, you know, the ocean or the water there is not transparent, and that just is essentially yet to be converted data. But our USD plugin can play the scene as well, which would then enable usage across many tools. Okay, I promised something about the Linux Foundation, or not the Linux Foundation, the Academy Software Foundation, which is a partnership with the Academy, Linux Foundation, and a number of industry folks. Intel is one of the premier partners. If you look closely at the pictures, I threw that in there. And we were one of the original premier partners in this. Why? Because everything we do in the studio industry is open source. So, again, lots of adoption for what we've provided. Take a look at this this video, which was shown at the SciTech Oscar Awards.
Creative filmmakers today rely
to tell
more
you
than
about
ever on engineers and scientists using open source
Everybody
software
loves Thanos.
to help craft fantastic visionary images.
Every single part of the filmmaking process is touched by software, and a lot of that software is open source software. Some of the greatest innovations we've seen in the modern era of filmmaking have actually been supported by open source software.
The Academy of Motion Picture Arts and Sciences and the Linux Foundation have created the Academy Software Foundation with support from industry leaders.
The Academy Software Foundation exists to provide a great home for open source projects that we as an industry use every day. Two projects the Academy Software Foundation is currently working on are OpenVDB and OpenColor.io.
OpenVDB is a volumetric data block format. It is pretty ubiquitous in use. Anytime we have an explosion, it's VDB. Anytime you have clouds, it's VDB. Anywhere where you have a lot of fluid simulation, fireballs, gas flowing across a surface, things that are big. We think there's value in having an organization outside of DreamWorks take responsibility for this. And I think we've already seen a benefit in that we've had other studios step forward in a way they had not previously with contributions to the standard.
I'm going to move on. I think you get the point. So the Academy Software Foundation is a curator of open source projects that that the industry wants to make sure stay on track, are supported and enabled. It doesn't mean that everything is going to be part of the Academy Software Foundation. For instance, at the moment, we certainly have no intention of just throwing Embree over the wall, for instance, or OpenSWR. But they are dependencies and utilized. But the idea of the foundation is to kind of coordinate and be a coordinating spot and a curation spot. I will tell you that not on the list there was OpenQ, which was brought up earlier today from Sony, is the latest project just approved about 2 weeks ago to migrate into the foundation. By migrating the foundation, that means they do the CI systems, build systems, and create the community and the definition around that using a standardized process. So it's a good thing. ASWF.io. Feel free to look it up. They're looking for participants all the time. They'll either take your money or you can just participate and do that. I'm going to quit. I'm running out of time, so I'll quickly move on. I talked about we just launched what's called our second generation Intel Xeon scalable processors. If you follow Intel stuff at all, that was also known as Cascade Lake. These are Xeon oriented, as I said, so far, Xeons and up are really strong rendering capable processors. The key things that you get out of the scalable processor, besides some of the new process capabilities, are what's called Optane DC persistent memory. The other thing I haven't hammered home, or if I should hammer home, is our ability to run any data set of any size as long as it fits in memory. So I talked about the 100 gig. About 4 years ago, we did a 10 terabyte, 10 frame per second Stephen Hawking data set. So as long as it fits, and it fits either in your local machine of 64, 128, 192 gigabytes, or collectively across. So the 8 nodes that I was showing, those running there, have 3 terabytes of data in it, and we could display 3 terabytes of data if we needed to. Anyway, many different SKUs that you're used to, but the key thing is the Optane persistent memory is a DIMM that goes in close to the processor, but it's persistent, so it actually can save and hold data. So it can either use to expand your data size or not. And then Deep Learning Boost is the first Xeon or first IA processor to have vector instructions for deep learning, and that increases performance. All the other ones are cool technologies there. Real quickly, we're not all about just rendering. We do support shading, and we've done a lot of work to optimize open shading language, particularly with Pixar and Sony. And all these optimizations, which have been worked over for 2 years, incrementally added, are now have hit the point of 80-20, where the majority of the stuff is in there. But we're close collaborators with the industry, with our partners. If you have a great idea, feel free to contact me or anyone else. But we're seeing 2x speed up on some shading scenes from Pixar, utilizing, again, things like our Xeon scalable processors. We also are also focused on cloud computing, and in particular visual cloud computing. We have a whole initiative called Open Visual Cloud. Intel Rendering Framework is part of that initiative. You can see the kind of workflows and the enabling that we're doing. You could think of it as Intel in a leadership mode for a variety of open source capabilities that we have and that the media market has. We announced a great partnership with Netflix on our open source scalable video technology codec that they are going to start to use, and it works very well, and we actually demonstrated it as a desktop environment, similar to a Teradici type thing. We did in your packets, in your bags, there is a discussion of how the V-Ray for cloud have put together with Intel's capability. So take a look at that. So if you remember this, what our goal over the next several years as we work together with the industry is to really reach for exponential changes and improvements in performance and capability, is on its way to you. The idea is to shrink those times, make offline render minutes, seconds, where you get the quality you need, turning around many more movies, whatever, and then driving that down from left to right so that you'll see ray tracing, just as Steve Parker mentioned, moving all the way into gaming and real-time capabilities. So that's one of our goals. How we're going to do this, I mentioned the thing XE architecture, X to the E architecture. You'll hear us use both of those. So X to the E is exponential. If you come up to me, you'll see this says Think Exponential on here. And so we're looking at creating capabilities across our processing elements to dramatically move the industry forward as we come out with new discrete Intel GPUs over the next several years. Very similar to our to other GPU vendors in the marketplace. We will have a variety of what we call SKUs or point products from client, laptop, whatever, all the way up to data center. Part of that plan, I announced this for the first time a couple weeks ago, is ray tracing acceleration hardware. I'd say similar to NVIDIA's RT Core, but it has really not exactly to do with that. But it is that kind of implementation where we are going to look at what the best, or are looking at what are the best things to accelerate in the ray tracing environment, particularly for data center, render farm, the traditional workstation up use, and in particular for Intel rendering framework. So what it is going to be is an Intel rendering framework accelerator where your investments like Corona and V-Ray and Moonray have made will get that exponential performance by adding one or more GPUs, Intel GPUs in the environment, and with little or no code change. There might be a little just to map to that, but it's not like some brand new thing that you have to do a whole new code base. Your CPU code base will be your GPU code base, and we will accelerate our current capability when the product becomes available. And now you're going to say when, and I can't tell you. Sorry. But we can talk about that later. And on top of that is the notion of a holistic platform view. Remember I told you CPUs are great parallel processors? That's not going to change. They're going to continue to be great parallel processors. They're going to continue to do very strong elements like the BVH build and other stuff that people talked about that are complex things may stay over on the CPU if that's the right thing to do. It's not all, it's together. So a holistic environment. And then the other thing is we are looking at building an ecosystem. So watch this. So very similar to what Yaroslav mentioned this morning, I actually have to go talk to him. We have research centers that are going to work with us on advanced features, advanced capabilities, and prepare research and capabilities that are ready for the marketplace when the products come out. If you saw the talk today by Phil, they were saying, oh, we've been working a year or two on the RTX thing and we're still working on it or whatever. Our goal is the day our stuff comes out, it's got algorithms, capability that the industry can use. That's actually one of the benefits of Intel Rendering Framework in general, is that of course we see the Intel products before and we optimize for them. And with that, those are the things. These are the takeaways. We've got some new software that we're always developing, OpenVKL. We've got the USD OSPRay plugin available. Check out our new scalable processors with the deep learning boost. As I just said, ray tracing acceleration within the scope of Intel Rendering Framework that we hope you are using or will come on to use is there. And then finally, an ecosystem is being developed, and we certainly would like to partner with you. And with that, I have run out of time. Don't know if they're going to give me any questions, but I am here through tomorrow. Look me up at James L. Jeffers. Yes, I call myself Jim, but unfortunately, it's not the most unique name in the world. But feel free to reach out. Check out these resources where you can learn more about what we're doing, and thank you.